Good morning, everyone. There's a neat little circuit right here. It's a polarity indicator that I put together. And right now I got 12 volts on the red wire and it's ground on the black wire. It's from an external power supply. Let's turn that supply on. We'll see which LED turns on. The green LED, look at that. Now, I'm going to power down, swap leads, so that now the black lead is on the red wire and the yellow lead is on the black wire. Let's see which LED turns on now. The red LED. Amazing. Now the reason I built this circuit, I have a polarity dependent coil, a latching relay, deep down inside a drive. And I'm going to attach these wires to the coil and we'll bring this board outside the drive and we'll be able to see what state, whether energized, latched, or de-energized, latched, condition it's in. So either this LED will be on or this LED will be on. And I'm not sure which one's going to be energized and de-energized. That's not going to matter. We're just going to know, for instance, like say energized latched will be the red LED, de-energized latched will be the green LED, or vice versa. And the reason I need to see the condition of that relay, whether it's latched energized or unlatched de-energized, is because there's intermittent alarm going on with that system, and I need to see what that relay's doing to determine whether the relay is the problem or not. Did all that come out right? That didn't sound right in my brain. Okay. Next thing I'm going to do is I'm going to unsolder that latching relay from the power board and bring it over here and hook it up, and we'll see if we can get it energized and de-energized, and we see what state that these LEDs are in at that moment in time. They power down, and I'll go and grab that latching relay. Here's the latching relay that I'm going to remove from the board. Now way back when, I thought this was a circuit breaker, but it's not. It is a relay. And depending, let me flip it over and we'll see here's the contacts right here. Here's the coil. And depending on the polarity of the 12 volts applied to that coil, like say 12 over here, ground over here, would be de-energized, and or 12 over here and ground over here would be energized. So this is actually a polarity dependent latching relay. And once it's in one position, you can remove that voltage and it'll stay in that position. So let's see if we can get this removed. Add a little bit of solder here to help the old solder to flow. Now what this relay's purpose is, it connects the positive output of the three-phase bridge rectifier to the positive terminals of the IGBT. I'll turn my iron up a little bit more. These thick traces soak up the heat from the soldering iron tip. So you have to turn your soldering iron up a little high to compensate for that heat loss. Add a little bit more solder to that one. This board wants to move around while I'm working on it. Did we get it? I think we did. Let's see here. Take some solder wick and see if we can wick that out. There we go. We got it out. Definitely could use some cleaning on this drive. Let's move that board out of the way. Let's test the relay. Alright, let's see what state we're in. We did switch it. Yellow wire over here, black wire over here. Let's see if we're energized. Bring my meter in over here. Okay, we're de-energized. Let's swap polarity on the coil. Put the black wire there and the yellow wire here. Okay, see it switch state by that little indicator. Let's see if we're energized now. Okay, we have good continuity too. 0.2 in the meter is my meter leads. Alright, let's de-energize. Other way. Okay, this is de-energized mode. Now you can manually flip this. It's kind of hard, but you can. That's why I thought it was a circuit breaker. Okay. Let's hook up our polarity indicator. Let's put, well, let's see which way we have to go first. Okay. We'll put the black wire right there. The red wire right here. Let me get me another couple more clip leads. so we can clip onto the coil. Let's put the blue wire right here, the black wire right here. Now let's see what we can do. See if it still works. Are we in the picture? Let me turn that light off so we can see those LEDs a little bit better. Okay. Now let's switch polarity. Okay. I've got it all hooked up for our test. I got the yellow wire from the power supply going to the red wire of our polarity indicator and going over here to one side of the coil. Got the black wire from the power supply going to the black wire of our polarity indicator and going to the other side of the coil. Now in order to change the polarity, I'm going to have to change it at the power supply. So let's watch that little tab right there. That'll tell us whether we're energized one way or the other. Okay, so we have the green light on, indicating positive 12 on the red wire and this side of the coil, and the black wire from the power supply going to the black wire of the polarity indicator and going to this side of the coil. Now I'm going to swap polarity at the power supply. Watch this tab and watch these LEDs. Okay, we switched polarity and our red LED is on now. Let's take power supply off. Okay, we're still latched in over there in that one direction and the LEDs are off. Let's swap polarity again. The green LED is on and we're latched in the opposite direction, either closed or de-energized or energized. I got to check which. Okay, let me stick my meter in here. I'm going to go on the contacts. Okay, with the green LED on, we're energized. Fancy how that worked out. Okay, I'm going to swap polarity again at the power supply. Red LED is on. We're latched in the de-energized mode. And it stays latched when you remove the power supply. Got to get everybody centered. Energized, green LED. De-energized, red LED. Energized. De-energized. Amazing. And it stays in the de-energized or energized position when you remove power. That's quite the relay right there. That is quite the relay. You know, that would be something you'd use if your unit was in a machine that was vibrating very badly to where a normal relay might become, the contacts might bounce from the machine movement. But this right here, it stays in that position when power is removed. So, I'll put the drawings of my polarity indicator up at the end of the video, and you can make one. It's very simple. Very simple circuit. Here's the back side of it. You have two relays, one resistor, one connector, and the perf board. Very simple. It probably took me 30 minutes to put this together. The hardest part was I had to drill the holes a little bit wider for this connector. There we go. Good morning all. Here's our polarity indicator circuit. And here is my circuit drawing. This is the 2-pin terminal board, the connector. Here's our R1 560 ohms, and here's our green LED and our red LED. Now when we apply plus 12 volts and ground, plus 12 on 1, ground on 2, we'll have current flow through here, through this green LED, which is forward biased. This side will be positive on the anode, and this side would be ground on the cathode, and it would emit photons. Now notice that the red LED is reversed biased, so we have no current flow through that. And the green LED would illuminate. Now if we put 12 volts on pin 2 and ground on pin 1, now the red LED is forward biased, plus 12 volts on the anode and ground on the cathode. And the red LED would illuminate. And notice that the green LED now, with 12 here and ground here, the green LED is reverse biased, so no current flows through there. Now we have to current limit these LEDs, because if you don't, they will burn up. If we put 12 volts without this current limiting resistor, if we put 12 volts directly across that green or red LED, they would not survive. You'd see a bright flash of light and then they'd never light up ever again. So you have to limit the current. And that's the purpose of this 560 ohm resistor right here. Well, how do you determine the value, the resistance value of that resistor? Well, we're going to talk about that next. Here's our circuit with just one LED, either the red one or the green one. Here is R1. Here is our voltage. I named it VBAT, V battery, because I got a battery symbol right here of 12 volts DC. Now, VR1, the voltage across the R1 resistor, and the voltage across the LED will equal 12 volts DC. It's Kirchhoff's voltage law. So the sum of these voltages equals the source voltage. Now up here, V battery is 12 volts DC, and V LED is 1.4 volts DC. Now that's an arbitrary number. It could be 1.8 volts DC, it could be 1.2, or it could be 2 volts DC. But I always pick 1.4 volts DC because it works. It works for me. Also, it could be 2.2 volts DC. We'll see here in a little bit when we power up this circuit and we analyze the voltages as compared to our mathematics. And I always use 20 milliamps as the current through the LED. So with these voltages and 20 milliamps through the circuit, we shall determine what the value, the resistance value of R1 is. So right here, I just threw this in here. V battery equals VR1 plus V LED, just like we talked about earlier. Now the voltage across R1 equals V battery minus V LED. That would be 12 volts DC minus 1.4 volts DC. And here's our equation. R1 equals V battery, 12 volts DC, minus V LED, 1.4 volts DC, divided by current LED, the current that runs through that LED, 20 milliamps. So 12 minus 1.4 divided by 20 milliamps. Here's our full equation with values installed. And if you pull out your calculator or your slide rule, 12 volts DC minus 1.4 volts DC divided by 20 milliamps equals 530 ohms. Now, there's a couple of standard value resistors that we could have used. We could have either used 510 ohms or 560 ohms. Those are the closest values to 530 ohms. I didn't want to overcurrent the LED, so I went with 560 ohms instead of 510. I think if we used 510, we would have 21 milliamps of current flow through that LED, or pretty close to it. Now what we'll do is we'll power up our circuit right here, and we'll measure the voltages, and we'll get true values instead of this 1.4, which I like to use. It's always worked for me when determining what R1 is. But we'll see what the actual voltage across these two LEDs is, and the current through the circuit. I want to try and get our power supply. I'm using an external power supply. I want to try and get that as close to 12 volts as possible. Phew. Looks like that's the best I'm going to do. 12.04 volts DC. Okay. Let's bring our circuit in. I'm going to put the 12 volts on the red wire, positive 12 volts, and its ground on the black wire. And we have the green LED illuminated. Let me see if I can get in here and measure across this resistor. Okay, we have 9.75 volts DC. Let's see if I can measure across that LED somehow. There it is. Okay, let me get my leads turned around. Okay, the green LED voltage drop is 2.217 volts. 2.216 volts. And the voltage across the 560 ohm resistor is 9.66 volts. Let me write all this down. Let's measure that again. Okay, there's 9.64 volts DC across the resistor. Let me write that down. VR1 equals 9.64 volts DC. And the voltage across the LED, that was 2.212 volts DC. 2.212 volts DC. It's VLED. Okay, now let's measure, if I can get on it. Okay, the voltage from the power supply is 11.85. 11.85 volts DC. That would be our V battery. Okay, let's reverse the leads and we'll see what the red LED's voltage drop is. Okay, I'm going to put the ground of the power supply on the red wire and plus 12 from the power supply on the black wire. Now the red LED illuminated. Let me differentiate between these. I'm writing all this down off camera. You'll see it in just a little bit. VLED, VBAT, and this is for the red LED. We'll have to measure the currents too. Okay. We have 9.87 volts across the LED, or I'm sorry, across the resistor. 9.87. I'll just go BLED. Okay, the LED voltage drop is 1.979. 1.979 volts DC. Here, let me reverse the leads and you'll see that the lead polarity, see that right there? The negative 1.978. We reverse the leads, we have 1.978. So let's go see what VBAT is. 11.84. Now let's measure the currents. Let me write that down. Current LED. Current LED. Set my meter to current mode. Milliamp current mode. And we'll put the meter in the circuit. Okay, I need another clippy lead. Now we'll get to see what the current is. Get back in the frame there. Oh, I'm in AC mode. Let's see. There we are. Okay, for the red LED, the current is 17.74 milliamps. Now we'll swap leads and we'll see what the current is for the green LED. Everybody in the picture? Okay, there's the green LED, and it is 17.32 milliamps. Now these are real world values from the actual circuit. That's amazing. That is amazing. All right, all. Thank you very much for coming over and seeing what we're working on next. I hope you enjoyed that. That was a lot of fun. That was a lot of fun. Fascinating to see how things work on paper and how they work in the real world. We'll see you next time.